35 divided by 69, and we multiply that times 4, and lo and behold, we get 3.18.
Really? That's pretty awesome.
Pretty sweet.
In lieu of a standard quick quiz, the Idealized Science Institute is celebrating Pi Day, which is on Thursday, 3/1/4. What we're going to do today is...
As I was saying, what we're going to do today is take you through some Pi Day activities to engage your students in dialogue and maybe get them excited about pi and math and how it connects to physics and all these other fields where seemingly pi has no business showing up. And you might have noticed that Dr. Wargo is no longer here. You could tell because I have a worse mustache. But if you're one of the 4 people that have watched the Idealized Science Institute podcast, you may recognize me from that. My name is Jake Becky, and I am a postdoc at the University of Illinois and a co-founder of the Idealized Science Institute with Dr. Wargo. So I want to take you through an activity that is meant to engage students of all ages from discovering for themselves a formula for the circumference of a circle, and that introduces this notion of pi as the slope of a line. So we're going to see that really briefly, because we want to get to more fun stuff where we use that formula and some other basic assumptions to derive the area of a circle. And then we're going to actually do a quick quiz where we delve further into estimating pi from these simple facts. Okay? So we want to motivate this for your students. You can say, the ancient Greeks, they didn't know this thing called pi. And for thousands of years, people were fascinated by shapes and patterns among them. And so we have circles with certain diameters and certain circumferences. And, the ancient Greeks maybe said, let's try and see if there's a pattern here. So you might have your students have a bunch of circular objects around the classroom, and you might just ask them. And you don't have to tell them. If you have time to let them decide how they want to present the data, you can ask them to present the data however they see fit. But you kind of want to guide them towards plotting it on an axis. This is a way that I don't think a lot of people think of the area of a circle, the circumference of a circle. But if you do this, what they'll find is, okay, they have some points, and maybe the first one's here. It's a rather small object. It has some small diameter that we put here, and it has some circumference. And then you'll take the next point, whatever it might be. I'm just making up the data, of course. And then maybe, let's say, one more further out for some large object. Right, and this isn't meant to be perfect, it's just representative of what you will encourage your students to do, and of course there's going to be measurement errors, it's not going to be a perfect line. But what we want is for the students to realize that pi is really the slope of this line, right? And you can call it pi, you can call it maybe something they're more familiar seeing, is you could write the equation of a line, which is typically y equals mx plus b. So this is a formula that most even middle schoolers are familiar with, and hopefully every high schooler is. And if not, this is the slope of a line, and then the y-intercept here. But we have the circumference and the diameter, so you want to encourage them to map this to c equals md. And if you have 0 diameter, you have 0 circumference, so there should be a y-intercept of 0. And now we have this formula. But the key thing is the students created this formula by experimenting and doing measurements on these circles and finding a pattern. So it's not just the memorization of some formula for circumference, but rather they have empirically derived it. So this is good for all age levels, and as we move past this, we're going to get into more and more advanced things. And maybe some students will push back and say, look, we already know it's pi, so let's just use the symbol. And you can decide how you want to navigate that, but I think it's okay. The point is, you can write down the formula, you just saw where it came from, you now have this new idea of pi as a slope when you plot circumference as a function of diameter, and our goal for today is to estimate that value of pi. So what we'll see next is how to start doing that from some very simple assumptions. Okay, on our next board we have the step 2 of what I think would be the natural progression from the circumference formula. Now that's accessible to students of any age. They can measure these things, they can plot data, so this is good for middle school and high school, but even high schoolers that memorize this formula maybe have never thought about where it comes from. So we want to start from that point, which we now have, I'll recall the formula. Circumference is equal to pi times the diameter. Now we have this, and we have another formula that I think students are very familiar with. and that's the area of a rectangle. So I will call this A, and I'll use a little square just to remind us that we're talking about, a quadrilateral here. And the area, as many of us are very familiar with, is just the width times the height, okay? Your students are gonna feel very comfortable with this. They will have just derived and therefore reviewed this formula. And now what I want to sort of guide them towards is how can we think from these formulas, how can we get a formula for the area of a circle? So I want you to pause the video now and think about this. If you haven't seen it before, it's not at all obvious, at least not to me, but we want to say just from these two facts, how can we get a formula for the area of a circle? So take a second now, pause the video, write down your thoughts, and then unpause, and we'll get started. Okay, so I've assumed you've taken the time to think about it a little bit. And at first glance, it's not obvious, right? If I just have this area, right, you could start to think about, and many students will say this, well, maybe I could shrink this down and put it inside, and then I know the area of that. So I know the area of the circle is just a bit larger than that. And then they might go down this route of trying to estimate or approximate the area of the circle this way. And these are great thoughts, and you can go down that route and start to get better upper and lower bounds using different regular-sided polygons. Totally valid way to proceed. But what I want to all of these different directions are valid ways of engaging your students in dialogue around mathematics and trying making this like an actual creative endeavor. But what we're going to be headed towards today is something a little different. So I want to think about, what if we can map a circle to a rectangle? What do I mean by that? So I want to say that I know how to compute the area of a rectangle, but I can't use that here. So if I start to reshape this, right, if I know the area of any one of these, I can multiply by 4 and I can get the overall area. Or maybe I can reshape things and see how maybe they connect here. So let's move this formula a little bit for ourselves. We'll say that this is C equal pi d. And I want to say this is going to be the case where, n, let's let n be the number of shapes we do. Let's say that's n equals 4. And what we might do, what one could do, is, and you can literally do this with your students, with actual pizza for Pi Day, if you wear gloves and are not worried about germs, or you can do it with pieces of paper, whatever you have around. It doesn't have to be expensive for them to engage with this authentically. And my pictures are not going to be perfect, but the idea is you would literally cut out the paper, you would reshape it, and you'd say, okay, now squinting at this looks a lot more like a rectangle. So then you push the students and say, how can we make it better? You let them think for a bit, and if they don't want to speak, really let them think, and the silence will eventually have someone say, well, what if we add some more divisions? And that's exactly where we're headed with this. And this is the way of thinking for the math teachers in the audience, or just people that have taken advanced math. You see maybe where we're headed with this. You can start to think of the idea of a limit. But here we have, let's say we have n equals 8 subsections. And now what does that look like? Well, again, my picture is not going to be perfect, but the idea is what I want to communicate. And so we're going to start getting something that starts to look even more like a rectangle, okay? All right, I hope I counted correctly, but we have these shapes. And what's going to happen if you take that limit to infinity? Well, as n goes to infinity, I won't even try and represent it, but what is it going to approach? It's going to approach a rectangle. So this already may be something that students have never seen or thought about, or even considered that we could use something we know about rectangles to say something about circles. So this might be very new to them. So you want to pause here, and now the key thing is, okay, that's all fine and good, but what is the height and what is the width of this rectangle? And now you have to let the students really try and think about this. So it's visual thinking. You have to think about what we're mapping from here, and some colored chalk can help the students see this. So let them think about it for a bit, and then what we want is for them, and you can have them come to the board and engage them in dialogue, and you step off to the side and let them take over. That would be an ideal scenario. And maybe they'll say, okay, let's do this quarter arc in green, and I see that that is now in green. So I'm just mapping it like that. And then you have to say, okay, well, what is this side length? Well, if I take this, this is going to be that one, so this is going to be that. And it helps with visual thinking, and now you have this, okay? And that trend is going to continue the same way. And so we're going to have an orange one there, and we're going to have all green here. Okay, so now we have to ask, what are these actual values in terms of the parameters of interest for our problem, right? We know we can just write the area as width times height, but that doesn't get us any closer to writing a formula for the area of a circle in terms of the parameters that we're interested in. So you want to push on the students and have them realize that this is a quarter of the circumference. So that means that now we have half of the circumference up here. And you can go ahead and do the same thing here, right? We have an eighth, an eighth, an eighth, and an eighth. And if you continue this pattern, so here, right, we're going to have the circumference over 8 times 4 is equal to the circumference over 2. And just like this, we're going to have the circumference over 4 times 2 equals the circumference over 2. And so you can motivate students to realize that this trend is just going to continue. And the limit of this is going to be the circumference over 2. Okay? That one is maybe a bit harder than the other one. This one, students very quickly see that's the radius. But we're going to encourage them to put it in terms of diameter, just for where we're headed. But they can just as well write it in terms of the radius. It's obviously just a simple conversion. Okay, so this is kind of amazing if you take a step back and think about it. We've gone from this was empirically derived in the first part, and this is like a very standard formula that people are very comfortable with. So with some very basic assumptions or empiricism, we now are ready to write down a formula for the area of a circle, only knowing these facts. And so we'll say the area of a circle is just the width times the height. It's the circumference over 2 times the diameter over 2. Probably not the formula your students are familiar with, but this is the whole point. We want them to stop thinking of these formulas as things we just memorize and start reasoning about how we can obtain them, or how someone could have obtained them before the advent of modern technology. So what do we have here? We have C d over 4, and then I want to take C, and I want to just plug in pi over d right here. Okay, that's all we're going to do. And so we'll have pi d, and we multiply by d, so we get d squared, all over 4. And that is the second equation that we are going to use today. We have now gone, let's take a step back and see what we've done. We've gone from an empirically derived formula for the circumference in terms of diameter, and a very well-known formula, and we've gotten a new formula. So this type of thinking is uncommon to a lot of students in math who are just told formulas, told to memorize them in some process and to identify when you use a certain formula for a certain problem. And this type of thinking starts to get them to step out of their comfort zone, and we'll see where we're going to take it is very cool. So with this in mind, we're going to step over to the next part of the video. Okay, and now on the screen, we're going to have the quick quiz that we want to engage our students. We want to use the quick quiz to engage our students in dialogue around pi. So a lot of people think of math as something, formulaic, and you learn some algorithm to solve some problem. But we really want to change that type of thinking, and we want to have the students reason through problems just like we have with all the physics quick quizzes we've uploaded. And so what the quick quiz says, as you can see, is we want to derive a formula that depends just on the areas here and gives us a formula for pi. Okay? So the quiz is, and you have your students pair off into groups or think about it for themselves first and then pair them off into groups. And you want your students to derive a formula for pi that only depends on the areas of the shapes drawn. Okay? And we intentionally left it blank. Okay, so pause the video, write down an answer, try it yourself, and list your confidence as always. Okay, we're going to assume that you paused the video, you gave this a go, and you listed your confidence. And now we're going to ask students to share their thinking. So some students, might say, okay, well, I know that this area is, let's say that's 4. And they often give concrete numbers. They say, let's say that's 4, and that's 4. So then I know the area of the square is 16. And so I know the circle must be smaller than 16. And that's great thinking, right? This is true. This gives an upper bound on the area of a circle. But you want to push a little bit and say, does that work if the width is 5 instead of 4, right? And you get them to the idea of labeling this side. And some might write it as X and Y, but you push a little bit further and say, well, we want to work in terms of the formulas that we just derived, so what might we call this width? And most students will be able to see that it's just the same as the diameter. So we can label this as D, and by the same logic, by symmetry, this is D. So the area of this square is d squared. And we can go ahead and have them explicitly write that down. And ideally, they will come to the board and write this down themselves. Now we have the area of a square. Okay, and then we recall from the previous board that the area of a circle, which we just led them into this, so the hope is that they will remember this. Let me not get it incorrect. We have pi over 4 times d squared. Okay, so we're really close. Now you have a number of ways, depending on where your students are at with algebra, they might immediately see what we're going for. Hopefully they will get this themselves, but you can guide them if need be. You just want to take d squared, and we know that it's equal to this, and we want to plug it in. And so what do we get? We get the area of a circle is equal to pi over 4 times the area of a square. So they've now derived this, mind you, from a very simple experiment, just measuring circles and diameters, and then using some geometric thinking, some visual thinking. And now we're at a point where we have an estimate for pi once we solve this. So let's do that together. I'll move pi over here. I'll do it in one step. But you're just going to multiply by 4 and divide here by the area of a square. So we're going to have the area of a circle divided by the area of a square. Okay. And this is what we were after. And you might say, why in the world did we just do all of this work? Well, even though the Greeks did not have computers, we now have computers with a lot of computation power. And this is going to guide students through a lot of different directions that you can take them from this formula. So note, this is an exact formula. This pi literally equals 4 times the area of the circle divided by the area of the square. And this holds in general. But what you then want to say is, how can we really estimate these? The area of the square is easy. We get out a ruler and we measure it. And maybe it's 5 inches. And we have 5 inches by 5 inches. We know that overall it's 25 inches squared in whatever units. But if we instead want to estimate the area of the circle, you immediately see all we could say is it's less than 25, or it's less than d squared. But if you happen to have some graph paper laying around, you might ask the students to draw this on a grid and start to think about using that grid to estimate the areas. So now we have this exact formula, but we've just moved the problem around because we want pi. That was our goal from the start of the video, but now we have areas. This one's easy, so I'll put a little check next to it. Very easy to literally measure, but the area of the circle is still difficult. But now that we have this set up, we can push a little bit further. So this might not be obvious to the students, but let's pretend that this is on some graph paper. And it won't be perfect, but that's okay. So suppose we have this. Now we're zoomed in on the graph paper, and we want to ask students now, how could we estimate the area of a circle? And doing so will give us a little squiggly here, because pi will now be approximately equal to whatever our approximation is on the area of the circle. And so we can look right here, and we can have the students come up with a protocol for estimating this. Some will say, okay, well, this is about half. So maybe I'll consider that half a square for the circle. This is maybe like an eighth. And you want to push back a little bit on this and say, okay, well, if one person looks at that and says it's an eighth and the other says it's a sixth, we're going to get different estimates. So you want to have them establish a protocol for how you're going to estimate the area. Because where we're leading them is we're going to iteratively refine this. So maybe we say, if the square has less than half, visually less than half, we're just going to say that that's outside, and everything else we'll say is inside. And you have the students come up with these protocols. They can have different protocols, but you want to have them verbalize this and commit to it. And then we're going to count and use these squares to estimate the area of the circle. So in this case, I'm saying that, let's use a different color here. I'm saying that 1, 2, 3, 4 are out of the circle, and the rest are inside. So we have 16 total. So we have an area of the total in whatever units. That's another key thing, is it does not matter what the units are. But what are we going to get? We're going to get pi is approximately 4 times the area of the circle, which we're going to say is everything that wasn't included in these. So that's 12, right? Divided by the total area, 16. Okay. And so let's reduce this. We have this as 4 times 3 over 4, okay? And we get an approximation of pi of 3. Now that should be pretty satisfying. And if students know pi, they're going to say, okay, we're in the ballpark. And then you say, how can we make this better? So pause the video, maybe it's obvious, maybe it's not, and think about how you could make this approximation better. And once you've thought about it, what you might realize is we really have an issue of scale. We have the circle drawn, and you drew it, the students are going to draw it somewhere on their graph paper. And then whatever scale they have drawn it as, that's what they're stuck with. So hopefully, some students might say, well, what if we made the square smaller? And that's great. That's the exact right logic. But the squares are fixed. So you want to push a bit further until they realize that we could either make the square smaller or we could make the circle and the overall square larger. And so you're going to encourage them to do that, and you're going to go another step. And we can simulate that just by adding another section here, right? This would be as if we drew a larger circle and square on the same gridded graph paper. And the picture is not perfect, but then you go through the same process and you repeat this. You count the number outside and you count the number inside, and you repeat this process. And what you'll see is that you iteratively get closer and closer to pi. And usually the students get really excited about this. And for people that have had calculus, you see where this is headed. This is the idea of a limit. This is the idea of an integral in 2 dimensions. This is really the key idea that you want to impart. So we might call this calculus without calculus. You don't need to know what an integral really is to understand the key idea. You chunk your space into small little area units. And as you make that smaller and smaller and add them all up, you get better and better approximation. And before we move on, we'll just say that this is sort of the end of what we wanted to say, that we encourage you to engage all of your students with. And now what we're going to give you are just some silly ways to estimate pi that the students might enjoy. Math doesn't have to be boring, and we want to show some things that we think are fun that you can extend this with your students. Okay, so we're back with this estimator for pi that just depends on the areas. And we had the students come up with a protocol using the graph paper to estimate the area of the circle, and then they were able to get iteratively better estimates of pi. And you can have your students break up, and some of them do a really large circle, and others do really small ones, and you look at the values, and you can talk them through these errors. You can also realize that a circle is symmetric, and some students will say, why are we doing this 4 times when we could really break it up into just 1 quadrant and then multiply by 4. All these are great ideas, and you want the students to come up with them. And if they don't, that's okay too, as long as you're getting them to actually share their thoughts and write them down and engage in dialogue with other students in the classroom. But okay, so now we have this estimator, and that's one way to do it, but we wanted to put our own little spin on it. And we want to say, okay, yes, we could use the area, but could we also use the volume? So at the beginning of the video, we saw a teaser where we actually used the volume of water to estimate pi. So let's see how we would get that. And maybe you can get your students to come up with this. We have area, we want volume. A lot of them are familiar with the formula for volume of length times width times height. And you just want them to get at, you already have this area, which is, has the dimensions of length squared. And you hope that they'll be able to come up with the idea that we want to multiply by h on each of these. And of course, you can always multiply by 1. And the choice of how you do that is what makes all the difference. But here we have 4 times the area of a circle over the area of a square, and we just want to multiply by 1, but we want to do so in a particular way. H over h is just 1, we can always do that. And now we're right at our estimator. So the area times the height is going to be the volume, and the area times the height is going to be the volume of the square region. So we have the volume of this circular region over the volume of the square region. This is going to be a new exact formula for pi. Where we have the h is just some height of this that we're going to add. And when we estimate one of these, we're now going to have an estimator of pi. It's not going to be exact, it's going to be approximate, but it's going to have your students thinking about different ways of approximating pi, and maybe they can come up with a lot of other creative ways to do it. We thought this one was fun, so we'll jump over to the lab tables and we'll actually show how this can generate an estimate of pi. Okay, so we just derived a formula, an estimator for pi in terms of the volume of this shape, where we have a circle inscribed in a square, and then what we did is we just 3D printed some sides on here so that it can hold water, and we can actually do this demonstration. And if you don't have the ability to 3D print something, there's a couple options. One, you could find some objects that fit pretty well together, or you can just do the area estimator with graph paper. And as we'll see, you can also extend this into some computer programming-based estimates of pi. But what we're gonna do, what we thought would be fun, is actually estimate this using the volume of water. Unfortunately, I'm a theoretical physicist, and so I do not do anything of this sort, so I was hoping my experimental friend could help out. So I think we are all familiar here with Dr. Wargo.
All right, hopefully we won't make too much of a mess. We'll end up filling this with some water. The problem is we've got the cohesive force between our water, and it really will give us quite a significant error if we don't take that into account. So I'm going to overfill just a little bit, and then we'll just swipe off any extra water off the top. It'll make a little bit of a mess, but hopefully we can get any kind of error to be reduced. I think that's good. So I'll take and I'll swipe this forwards. And I'll go each side. Makes a little bit of a mess, but we really don't want anything overhanging. Okay, I think we're in good shape here. And then we'll just use these syringes and we'll suck up the water and we'll put them in these beakers and then we'll have the volume. So I'll just start filling these. And I'll push this in. And once we're done, we can just calculate.
Yeah, and so students, you know, you could ask them to come up with other estimators for pi based on other things that you could measure. And, you know, it's just a way to try and connect the fact that math and estimations and all of these things, which we use in physics all the time, are you know, intimately related. I think a lot of students think of math as one class and physics as another class and whatever science as another class, but really they don't, these separations are not always beneficial. And in fact, I think bringing some of these ideas from our physics quick quizzes into the math realm will be really helpful for students to connect these. And so
this is a first approximation. I'll get the last little bit of water out from each one of these, because now I can tilt it to the side a little bit and get the very last little bit. Try to get
we encourage you to think of other experimental designs. This is something we thought would be fun to do, but there are certainly better ways of building these in ways that you might be able to have some little latch that you could let all the water out. These types of things could be improved upon, but we just wanted to make something maybe a little bit different than other estimates of pi we've seen.
All right, I think that's all the water we're going to get out.
Okay.
I'm going to switch glasses so I can, these are really hard to read. So do you want the big or small one first?
Yeah, so now we need to think about it. The formula is 4 times the volume of the circular region times the total volume. So we need the circular region first.
That is 55.
Okay, we got 55.
And this one is,
Go ahead and confirm. Yeah, about 55.
looks like 14.
Okay.
Wait, let me get a better estimate. 14.
Okay, so we add those together for a total of 69, and we have 55 divided by 69, and we multiply that times 4, and lo and behold, we get 3.18.
Really? That's pretty awesome.
Pretty sweet.
That's,
so,
you know, I mean, for not being perfect, we still have a couple drops that we can't get out. That's incredible.
it's pretty decent, and I think students will be really excited to see all of these things that seem unrelated giving some estimate for pi. So we'll wrap up with some ideas of how you could extend this into long-term math projects that your students could take a deep dive into some of these ideas. But this is, you know, our idea for Pi Day, so we hope you enjoyed it as much as we did.
Yeah, this is great.
And what we did today was just hopefully a fun example of how you can engage your students in some activities for Pi Day. But what we really want to encourage at the Idealized Science Institute are long-term projects. And so I'm gonna put up here some things that students could delve into. And we might make some videos guiding teachers through some of these so that they can in turn guide their students. So the first one is something that we were kind of skirting around through the whole video, and lots of people have made videos on this. It's called Monte Carlo simulations. So you'll randomly sample points, and those points will be, you'll put the square and the circle on a coordinate axis, and you'll randomly sample points within the square. And you just simply write code that will count the number of points inside and the total number of points, and you'll divide those, and you'll multiply by 4, and that will be your estimator. This is called Monte Carlo sampling. It has a lot of applications in physics. When you have something that's really hard to actually calculate, sometimes you can use these techniques to estimate it to really high precision. So this is a standard video that you'll see out there, and so we didn't want to focus on it, but it's a great long-term to start getting students into thinking about how you can use computer programming to interface with math and all of these things. Or you could do it with your whole class, all the same. The other one that we'll show is the Archimedean approximation of the area of a circle. So Archimedes had this idea that I'll inscribe a regular polygon inside the circle. Let's say you put a square in first. And then as you see, as the number of sides increases, we get closer and closer to the area of that circle. So this is, again, a great way, if you have a geometry class, you can encourage your students to start thinking about this. And you see that the area from a square to, a hexagon, the area is increasing. And this is going to be a monotonically increasing. It's only going to increase this function of area. And so it's going to get closer and closer and closer until an infinite-sided regular polygon would just be a circle. So Archimedes realized this a long time ago, and you can bring in the history and some of the philosophy of math here. It's really, really good. So you can take your students down any of these paths, and these are just some ideas. They don't need to be, you don't need to take up your whole course, but you could encourage your students to dive deeper in a long-term project. And there's no reason that they can't do this in math and any other subject. So we hope that you found these as interesting and as fun as we did today. And we hope that you will come back next week for more content from the Idealized Science Institute. And yeah, happy Pi Day, and thank you.
Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.